This is a Heathkit SB-104, vintage 1975 single sideband transceiver. Pretty impressive for a kit, and it has a following. It's a pretty radio, that's for sure. It has a lot of curb appeal, but it's got numerous flaws. One of them being the VFO stability. Boy, the thing drifts, and it's a little mechanically flaky. It's got dueling 7-to-1 reduction drives before it drives a variable capacitor inside the VFO. Let's see if we can have a look at that. This is the VFO down here. Oops. There is the VFO. And I don't think we'll be able to see the reduction drives. Oh, we can. Yeah, I recognize them. You may not. Anyway, the VFO wanders, and it makes a better temperature sensor than it does a VFO. It's really pretty annoying. So the thought was, well, let's replace the VFO with a direct digital synthesizer. Just a shaft encoder, a small microcomputer, and an analog devices direct digital synthesizer chip. Nice idea. Well, let's see how it works out in practice. Right now, we have no input signal to the radio, nothing connected to the antenna. I turn up the volume here, and what we're going to do is tune from 14 to 14350. Let's cover the whole 20-meter band and listen for what happens. That's a birdie. That's due to the counter that's counting the frequency, I believe. That's probably a harmonica, the VFO beating with something, because the tuning rate is really quick and very unstable. So it's got about 3 times the rate of tuning as the normal base frequency. More counter. Very weak something or other. Counter. That's kind of another harmonic. I believe that's the 3rd harmonic of the VFO. That's a pretty strong one. That's the strongest bird on the block. What was another one? I missed it. Doesn't matter. There. Another harmonic of the VFO. And we'll stop at 14.3. Okay, actually, not bad. As far as the birdies and spurs go, it's quite usable and only slightly annoying. All radios, or maybe not all, most radios have a problem such as this. Now what we're going to do is we're going to switch to a signal for the VFO that comes from a Hewlett-Packard signal generator. So I'll show you the generator. It's up here. And it is going to generate the same level over the same frequencies, and the level is shown on the scope in the background here. That's approximately plus or minus a volt, so it's 2 volts peak to peak. Now I have to change the rear panel here. There's a connection that connects the VFO that's internal to the rest of the guts of the radio, and it's this little jumper here. And I'm also tapping off this jumper to monitor the signal level, okay? So what we're going to do is unplug the jumper. That disconnects the internal VFO. And as you can see, the signal went to 0. We'll show you that flat line on the scope. And then what we're going to do is connect the signal generator, the HP signal generator, to provide a signal. You see the signal on the scope there has occurred again, and it's the same amplitude. And now let's crank this around so you can see the front panel. Hey, by some coincidence, it's back at 14 megahertz. That's not a coincidence. But now I can tune the radio by changing this signal generator frequency. So we'll go up again, and I'll turn up the volume. And we'll look for spurs again. There's a counter. Bear with me. Not sure what that is. Maybe a harmonic of the signal generator. It's very stable compared to the VFO, though. And if you're watching the scope, you see it's a very nice sine wave, of course, because it's coming out of Hewlett-Packard signal generator. There's a counter again. Right, we'll get all the way up here to, well, wait a minute, 14.2. We should have had a birdie here. There it is. Yeah, a harmonic, I think, of the signal generator again. Okay, or at least the mixer in the radio is mixing a harmonic of the signal generator. There's another one. Okay, all the way up to 14.3, and we'll call it quits. All right, again, quite usable. The important point there was you can replace the internal VFO with an external VFO. Same amplitude, same frequency range. It behaves the same really as the internal VFO, although the stability ought to then be that of the external VFO, because the rest of the radio is made with crystal oscillators, so they're pretty stable. All right, so we're back to 14. Now for the coup de grace, we're going to connect the digital synthesizer here, which is out here on the bench, shaft encoder, PIC processor, analog devices evaluation board. This is an amplifier. This is an attenuator. Amplified up and then attenuated a bit to get exactly the same signal level, or close to it, into the radio. So what we're going to do now is disconnect the signal generator. Let me move this back here so you can see the scope. Disconnect this. And now connect it to the DDS, direct digital synthesizer. And now we're connected, and again you see a very nice sine wave. Yep. And we are not quite on 14 megahertz, but that's because the shaft encoder was bumped. And I'm going to change it to 14 megahertz. There we go. The radio, that is. This is really 5.5 megahertz, give or take. Okay, now here's the bad news. You're hearing that? Oh, that's nothing. Oh, look at that bad boy. Wow. It's even moving the dead psychometer. I mean, these things are S4, S5. What's this one? Whatever. The point being, it's useless. It's stable as a rock because it's crystal synthesized DDS, but I mean, you can't use this. It's ridiculous. You certainly can't use it as is. I think you get the picture. I don't have to go much further. I don't have to go any further. I mean, it's horrific. Close up of the psychometer here, if we can get one. Too much light. Anyway, you get the point. So this is what you called a failed endeavor at this point. Can it be remedied? Yes, because I've used DDSs before in radios. But they've always been in conjunction with a phase lock loop. And the phase lock loop on my other radios that I've designed and built has usually been in a configuration where it multiplies the frequency of the DDS. I don't want to get into the details, but the point being that they all had a phase lock loop. Well, it turns out that the side benefit, and it's significant, of the phase lock loop is it's basically a narrowband tracking filter to clean up the crap coming out of the DDS, which is totally predictable, actually, because it's a 10-bit D to A converter. And that, by its very nature, generates these sidebands. And we can just briefly go over here to the simulation. And I'm using a tool called Simulink. And we'll get the camera on it. I don't know how well this will work. We'll cut it out of the video if it doesn't work. Where are we? I can't tell. Okay. All right, we're sort of there. Okay, we'll get this out of the way. Get this up. All right. So the spectrum on the left here is the spectrum out of a 10-bit DDS. You note all of these spurs. The spectrum on the right is the DDS after it's been passed through a phase lock loop cleanup filter. And the model that's creating this is over here or under here. And this is Simulink. Don't bother trying this in Spice. Don't bother. All right, so there you go. There is a fix. I'm not sure I'm going to implement it because I don't know how much I love this radio. Time will tell. But the direct digital synthesis as is utterly useless. Signing off, I think. Over and out.